Introduction to Dynamics of Polynomial Automorphisms of the Plane.
Well, thank you. I will try to tell a little bit about the dynamics. Oh yeah. Sure. No problem. Okay. Can you hear me now? So I want to do just a few things, and in fact, there isn't much known, so there isn't much to tell. But I can also, if you have questions along the way, you can stop me and slow me down, because if I don't cover all of my stuff, Serge will cover it. Okay. Well, let me see now. So I want to look at the this family of mappings. Okay. So this is a mapping of C2 with variables x and y to itself, polynomial, and has an inverse. The degree, I'm going to maybe sometimes actually spell out DEG for the degree of P, but P will be a monic polynomial to whatever degree it is, plus other things. Now, I want to focus on these mappings. There's a paper of Friedland-Milner that says if you're going to study the dynamics of polynomials over C2, basically you're good if you can understand these mappings. So I will just stick to these mappings and be happy. Now, Misha was mentioning periodic points. So let me first iterate this guy. So if I iterate this n times, the variables x and y are treated differently. In the first coordinate, x is raised to some power, and x, if x is large, it gets much larger. Y is just treated linearly, and then the first coordinate becomes the second coordinate. So what will happen is when we do this, we're going to have the iteration of p plus a bunch of lower order things, and then the second coordinate will be the previous guy. So this second coordinate will become p to the n minus 1 of x. Okay? And in particular, the degree of f to the n would be this degree to the nth. And if you ask about the periodic points, okay, so this would be the set of f to the n of xy equals xy. Okay. Well, Friedland-Milner showed that there's basically you use a Bezout theorem, and this number with multiplicities is going to be the degree to the n. So if you count multiplicities, then you know exactly how many periodic points you're going to have. Now, as Misha was pointing out, for the development of the one-dimensional theory, Montel's theorem was a wonderful tool to use, and the unfortunate news is that in 2 dimensions, there are versions of Montel's theorem, but they don't apply in the way you want them to apply. So Montel's theorem is a missing tool. And so, in fact, it turns out that you can get, well, before I go to tools, there's one other thing I wanted to say. So another thing is here, if I'm looking, I have a filtration picture. So I'm just looking at modulus of x and modulus of y. So if I'm given a map F, I can choose some sufficiently large number r so that I have the following thing. So I'm just looking schematically at the plane. So in this region, when x is bigger than y, you can see that when you apply the mapping F, you're taking fx to some large power, so it gets much, much bigger than y. So whenever you're out here, you're going off to infinity. Okay? So you're going off to infinity very fast, in fact. If you are in this region, if you're, in other words, where both modulus of x and modulus of y are bounded, it's possible to stay in this region. It's also possible to leave. Okay? And over here, if you're in a region where y is bigger than x, well, you know, if y is bigger than x, it could be, you know, x goes to x. I mean, when we're looking here, then this becomes the second coordinate. It could be that this stays, you know, this could be staying less than the second coordinate. However, it can only happen finitely many times. So I'll just put a little thing like that. If I'm in this region where modulus of y is bigger than modulus of x, I could stay there finitely many times, but I have to leave. I either come down to this region or go to that region. Okay? So the picture is a little bit more complicated than one variable. In one variable, you have a disk. Once you pass, you know, there's some disk of radius r. Once you're outside of that disk, you zing off to infinity. Here you have a little more choice about what might happen. So following the one variable case, we could have k plus. This would be all the points x, y, such that when we iterate them, we stay bounded. Well, anyway, n is 1, 2, 3. Okay. Now, I want to now look at behavior for the inverse. This is a polynomial mapping. It's a automorphism. Its inverse is polynomial, and its inverse has something similar. F inverse would look like y, what is it, p of y minus x over delta. Okay. If this isn't right, then it isn't far wrong. So we could also look at the orbit in backward time. In backward time, we have exactly the reversed picture. In other words, so for F inverse, we could stay here finitely often for finite time. But then after we leave, we'd have to go back here or there. Here we could stay finitely often. If we leave, we have to go up and in. So the inverse is exactly the backward picture for this filter. This is called a filtration. So filtration means we've partitioned our dynamical space in such a way that we have the various behaviors between them. So we have k plus. Okay. Now what can we say about k plus? Whoa, this is great. Beautiful chalk. Thank you. Whoever put this here, thank you. So here, so you can say that the set k plus has to be in this region. Okay, k plus has to be here because I can't. The only thing I know for sure is I cannot be in this region because this region goes off to infinity. So there's also k minus, and that would be where the backward iterates stay bounded. And so the k minus would have to be maybe a little bit green. Well, maybe they're not so different. Anyway, so k minus would be like this, and k plus would be like that. All right. So this would be analogous to the filled Julia set. Then there would also be j plus and minus, which would be the boundaries of k plus and minus. And so there's another picture that's worthwhile to draw. These pictures are all sort of symbolic. Okay. So here you could think about k plus as this way, and I could think of k minus like that. Okay. The boundary, so what happens in here, if I am outside of k plus, I know that I have to go to infinity and forward time, so I should think of, well, let me see. I love colors. Sorry, can't stop myself. Okay, so we're going to have a sort of, outside of k plus and k minus, we're going to have this sort of thing. Okay. Okay, so outside of the union of k plus and k minus, everything is swept away to infinity, either in forward time or backward time. Okay? So everything is transient outside of k plus and k minus. Now,
skinny. Does that mean you're making some assumption about delta?
I'm just making it, so it's a theorem. A theorem, Friedland and Milner showed that if delta is less than 1, then k minus has to have 0 measure. Okay. However, if delta has modulus 1, well, let me not get into this. But anyway, so this is one case. So when in the dissipative case, k minus always has 0 measure. Okay? So it is I'm actually drawing a theorem, as you're pointing out. A theorem of yours. So what happens if I am inside of k plus, inside the boundary of k plus, I stay inside the boundary, and actually I have to come down here. Okay. So in this particular case, k plus happens to be k minus. J plus, well, here is the boundary of j plus. I mean, k plus is j plus, the boundary. And so there are two sets that are interesting here. K is the intersection of k plus and k minus. So these are all the points in here. This is the set K. So these are the points whose orbits are bounded in all of forward and backward time. And there's also J, which of course you would make, in parallel with everything else. What is important here? Well, a theorem is that the Julia set, J plus, is the forward Julia set for F. Okay? What does that mean? Well, I've already told you that if we're outside of k plus, we go off to infinity. I mean, that's what the filtration tells us. We go outside of k plus, we go to infinity. So that counts as normality because we're going off. One of the possible things in normalities you're allowed, if you go off to infinity, then it's a normal family. Another thing is that if you're inside of the interior, you're going to stay bounded. Okay, you come in towards k, so you're going to stay bounded. So away from the boundary, you have a normal family. On the boundary, what happens? Well, if we're on the boundary right here, there's a boundary point, I'm coming right into there. Okay? So that is one kind of behavior. But in, arbitrarily close, I'm going to go off to infinity. So there is no open set here where you have a normal family. Things rip apart. So I have a set J plus where it's not normal, and also J minus is the backward Julia set. So if I think about it here, I've got the complement of J plus. So this is the set where I have normality in forward time, and if I look at this, this is the set where either in forward or backward time I've got some kind of normality. Okay, so at least half normality. In other words, either forward or backward time or both. And so J is the set where you're not, so the complement here, J is the set where you're not normal either in forward or backward time. So if I'm here, some point here, then I know that in backward time I'm going to, nearby points going to infinity in backward time, and they're nearby, I guess I said backwards. There are nearby points going to infinity in forward time and then backward time. So J is the set of points that are not normal in either time direction. Okay. So what I want to do is let me see. I made a mistake of having two sets of notes, and I'm not sure which set of notes I'm supposed to be following right now. So we're lacking, as I said, we're lacking Montel's theorem. So what we're going to do is it turns out there's some other technology we can use. And I want to use some potential theory which involves measures and currents. And so, so let me just recall measures. So what is an atom for the space of measures is a point mass at a point. So if A is a point, the point mass at that point is an atom for measures. And in fact, what I want to do is think of it also as a current of integration. So I'm thinking I could consider it that way. What is an atom for current? So this will be a zero-dimensional current. Okay. I could also have a complex disk, so for currents. So, I mean, I'm sort of disrespecting zero-dimensional currents and just calling them measures. An atom would be a complex disk. So what is a disk? I have some holomorphic mapping from the unit disk in the plane into C2, well, to something I'll call D, which is inside of C2. So this is a holomorphic mapping. And I'll just call H of D, I'll just call it D. And so I could have the current of integration over D. Okay? So what are currents in general? A K current is an element of the dual space of K-forms, or of compactly supported K-forms. Test means they're smooth and compactly supported K-forms. So since Dennis is not here, I can safely say that people very often refer to currents as K-forms with distribution coefficients. So I'm thinking of generalized functions being distributions here. A K current you can think of as a K-form with distribution coefficients. This thing here would be a 2 current. And if I pair it with some test 2 form, that's exactly just taking the 2 form and integrating over my set. Okay? So this is the current of integration. That's a current of integration. That's a current of integration. And so and in general, if you have a current, in general, if T is a K current, we take it and we can pair it. Okay? And the reason we want to use currents, well, there are different reasons, but one reason is that there's a sense of convergence. You say that a bunch of currents converge to some other current if whenever you pair them with a test form that converges. So we're largely interested in currents that are given as currents of integration, but those are sets, and when you're looking at sets converging, what's the sense of convergence that you know? Well, sets are sets. I mean, you could talk about Hausdorff distance on the set of compact sets, but the Hausdorff distance is not necessarily the thing that you want to have. So here we can look at things converging and have a different sense of convergence. So what I want to do is redo Brolin. I mean, you saw that you could do Brolin for a thesis. Let's do Brolin again. So how do I want to say Brolin's theorem? So suppose P is a polynomial. P is a polynomial in X. How could we say this? Well, we have a point z0, well, I'll call it x0, okay? And we're looking at the pullback. So we were taking the pullback. Okay, so I'm thinking of the point mass at x0. I'm going to pull it back. Well, in fact, this is the same as what you'd expect. is just the set of pre-images of x naught, and then take the current of integration over that. I normalize it, so divide by d to the n, divide by d to the n, and then this thing converges to harmonic measure. Okay? That was what Rollin's theorem was in disguise, just changing my language a little bit. You get something converging to harmonic measure by doing that. So if I want to do this for, let me just see if I'm forgetting anything that I wanted to say here. So let me state a theorem which would be two-dimensional Brolin. Okay. And that would be, what is x naught here? Okay. Well, of course, as Misha said, there could be, there is a possibility, there are a couple of exceptional cases where you have to, might have to avoid, forget the exceptional cases. You're taking a point in C. How should we be looking at that when we want to work in C2? We should just think of this as a codimension 1 algebraic set. So codimension 1 algebraic set, you want to let A be an algebraic curve. Inside of C2. Okay. Then what we do here is we take 1 over the degree. We need to normalize it. Take f, pull it back. Pull back that current. And this is the same as normalizing. I'm just going to copy f to the minus n of a. Okay. And this will converge. So let me see. I need a little more space here. The theorem says there exists a current mu plus such that for every, so let me move up here, for every algebraic curve, this thing converges to a multiple of mu plus for some positive c. Okay. So I guess part of my message is that when you're doing dynamics of this Henon, these are the Henon maps, if you're doing dynamics of this family, you are always finding yourself ending up on some transcendental object, but it's not so far from being algebraic. Okay, so let me see. So of course this leaves completely unanswered what is mu plus. The thing is here, if you have an algebraic curve, if you pull it back by this mapping, you multiply, in general, you're going to multiply the degree by d. And so that's why you normalize it by dividing by the degree. You want to, of course, here A is a curve with its degree growing very rapidly, but if you divide by the degree to the nth, you bring it down back to mass 1. In fact, speaking of mass, I forgot to mention what the mass, there's a mass norm. Okay, so there are two things going on that I forgot to say. Good thing I left myself some space. So what's special about this 2 current that's integration over a disk? First thing, you say that a current T, I'm thinking of a 1-1 current. So this is a, this is dimension, real dimension 2, and since it's complex, it's a 1-1 current. This is positive if whenever you take T and pair it with a positive form, you get something non-negative. So what's a positive form? Okay. So I take any test form that's of type 1, 0. If I take alpha and just wedge it with alpha bar, I actually get something imaginary. I have to fix up the I by multiplying it by another I. So this is the definition of something that's positive, and integration, the current of integration over some complex disk is a positive current.
With compact support?
Yes, yes. it's important, their compact support. Now, I guess there are a couple more things I want to say about these. Let me just say it over here. The other thing is one of these beautiful results of complex analysis. I want to have the mass norm. Okay, which I could give the definition, but let me say it this way. On positive forms, okay, if I'm looking for the mass norm on positive currents, the mass norm of T is just, the mass norm is given with respect to some metric. It's not metric free. And so I would integrate, I just pair T with the Kähler form. Okay. Now what do I want to take for my Kähler form? Oh yes, and if I take T and wedge it with beta, I just take this, and I can wedge it with beta, so if I can think of T as a matrix I can think of it as a matrix of distributions. If I look at it this way, I'm going to be basically taking T11 plus T22. Okay, this is if I take the Euclidean Kähler form, I'm just taking the trace. And if T is positive, so it's a theorem now, if T is positive, the TJKs, all of these guys here, TJK bar, are rad-on measures, signed measures. Okay. In other words, I started off making a very general definition. Distributions can be pretty complicated, but when we're working with positive things, you're just working with signed measures. So in fact, when you're looking at positive currents, which is, for instance, this case, you're just looking at the convergence of measures, the sort of the usual weak star convergence of measures. Oh yes, and in case I'm looking at a disk, the mass norm of the current of integration over some disk is just the area of the disk. So it's a nice thing.
The Kähler form does not have compact support?
The Kähler form does not have compact support. And so what happens when I'm... Okay. Okay. I think I need to respond to the voice of honesty. So let me expand my life just a little bit. Here is C2. I want to put things inside of P2. Okay? And so what is my let me put C2 down there. Okay? So what am I doing to make P2? I'm adding a line at infinity. Now, if you look at the formula here, when I'm going to look here at the x-axis coming out through infinity, then the y-axis comes out through infinity. So this is y, and this is x. So when y is very large compared to x, you can see that it's not clear what's happening. If I extend this, I can extend this to a meromorphic or a rational mapping of P2. And when I do that, I guess orange is a good color for danger here. This would be a point of indeterminacy. Okay? And this point of indeterminacy blows up to all of L and all the line at infinity. And so if I take the line at infinity minus that point, it gets mapped to this point, and this the indeterminate point gets blown up to the whole line at infinity. So actually, it's a theorem that if I have a positive closed current, oh yeah, I forgot to say also closed. Sorry, closed. Okay, closed means dt is 0. Okay, that means it's closed, which means that if I take t, this is the action of t dt on some one form is given by this formula, and that would be saying that anytime I put t against something closed, something exact, then I get 0. Anyway, the point is here, this extends to a current on all of P2. Okay? And what I want to do is actually take maybe the Fubini Studi metric on P2. Okay. So actually I was implicitly considering a current on all of P2 acting on the Fubini Studi metric in P2. So what does this say? So I want to give a little time to discuss what is the interpretation of Bernoulli's theorem. Well, here we have I'm sorry, I think I made a mistake here. My mistake is that I write notes and I don't read them. I should have read my notes. Okay. So this is one statement here. There exists a current, and everything converges to it. And the other thing is that the support of this current is J plus. In other words, if all the algebraic curves converge as currents to mu plus, I mean it's a unique thing, and just the fact about its support is it's actually J plus. So what this tells me here is that suppose I'm looking at this picture here. It's just a nice picture to focus on. Suppose I take some open set that intersects J plus. So here is this thing here is J plus. Okay. So if I'm converging to some current and my support is on J plus, what I know is that the mass of this f to the minus n a, whatever I've got there, in other words, mass means area, this is going to be bigger than some number, epsilon positive, times degree to the n. In other words, in order to be able to, what does my algebraic curve have to be doing here? This is J plus here. My algebraic curve needs to put some mass on U, so that means that it has to be coming, the amount of area that is on U has to be at least this much. Okay? And if I take some other open set, V, this disjoint, okay, I know that the mass, or the area, mass is area, the area of f to the minus n a intersect V times d the degree to the minus n, that's got to go to 0. Okay? That's what Bernoulli's theorem says in this case.
Sorry, is that this statement, the support of mu plus is equal to J plus, or
Yes.
containing
Equal to, exactly equal to.
for every algebraic curve?
There is some current, okay? And maybe I want to also restate my theorem in just a second here. So let me put it this way. Suppose I let d plus 1. Let this be all the positive divisors. Okay, just taking linear combinations of these guys, say. With total mass 1. So I'll call that T. T wedge beta with the mass of T being 1, in other words, weighted area being 1, then if I look at the mapping that is pulling back by F star and dividing by the degree, that maps this thing into itself. Okay? And the statement here is that mu plus, maybe some multiple of it, is inside of, is the unique attractor for D1 plus. In other words, everything in this set is attracted to that point. So you've got some current that attracts all these things.
That constant depends on the curve or maybe?
Yes. See, right, exactly. Right. However, yeah. So maybe I should say unique attracting ray. Maybe I didn't need to. Let me just say D plus. Forget the mass. Okay. Have a unique attracting ray.
So in this case, this is a theorem of reference margin.
Oh, yeah. More recent than Brolin. So let me give a corollary that I think is sort of interesting. So for every algebraic curve, the first thing is if I intersect k plus or minus, this is compact. Second thing, if I intersect k plus or minus, that's non-empty. And the third thing is that A is never inside k plus or minus. Okay? So this is what I was meaning by these things being transcendental. If I take this picture and redraw it over here, I'm not going to go to near infinity along the x-axis, but I could have something or other like this. But the point is, if I look at the y-axis, so this could be k plus, say. It'll go out to infinity here. If I look at how it intersects the y-axis, say, it's going to intersect, it has to intersect it, but only in a compact set. And it has to intersect the x-axis in only a compact set. And every other variety, no matter what algebraic variety I do, it can't avoid k plus, and it can't lie in k plus. So, but it intersects k plus, but that's only a compact set. Okay. So I think that's sort of a amusing. It's a corollary. Now, how do we get to this?
Can I ask a question? Are there like special cases where one can actually work this out? Like, I mean, no.
They're actually, so in other words, Misha showed us z squared.
Yeah.
Beautiful. Okay, there's the z squared. Your Julia set's a circle. There's a Chebyshev polynomial. Julia set's an interval. There is no such thing here. Although to say that there is no such, I'd have to sort of state more precisely a theorem. But you know, but then again, in the one variable case, there's a theorem that says if you have a tangent someplace, and let me see tell me if I'm stating it correctly. But if your Julia set has a tangent someplace, then you're one of those two examples. Okay. With these things, as far as I believe, I think it's already proved that you can't have a tangent anywhere. So J plus cannot have a tangent. However, it does have some structure. It does have, it's not a lost cause. But yeah, I'm sorry to say that if there was a nice thing, I would have shown it to you.
So, but in your convergence theorem, A is a local manifold in this corollary, A is algebraic?
Oh, sorry. So A, algebraic. For an algebraic curve. So algebraic curves are very globally constrained.
But for convergence you need in the case of algebraic, A is just some piece of
analytic manifold.
Let me give, so you're hitting on what should be interesting theorems. There should be other theorems that should converge to mu plus. I mean other theorems that are other objects, other, you know, disks or whatever that should converge to mu plus. In fact, since you asked, I'll just jump in and do that. Okay, so this is Brolin. So what is a saddle point? So a periodic point is f to the n of some point q is q, and this is a saddle point. The definition of saddle point is that if I take the derivative of f to the n at the point q, it'll have a couple of eigenvalues. Okay, and this S stands for stable. That should be less than 1, and the unstable guy should be bigger than 1. And then there's the stable manifold theorem. Says that there is a stable, you know, if you have a saddle point Q. So if I have, from my discussion, if I have a periodic point, I can just replace my discussion, replace f by f to the n. Just let me fix a point, replace it f by f to the n, and I'll have a fixed point. And I'll have some eigendirection for the stable, some eigendirection for the unstable. Okay. And so the stable manifold theorem says that there's a manifold. Okay. This is a theorem that's true in large generality for smooth mappings, but in this case we have a holomorphic mapping or a polynomial mapping, but I'll call it holomorphic mapping because in this case this is a holomorphic curve. Okay, holomorphic curve means I'm going to have some parameterization. Oh yeah, also there's the unstable manifold. So, oh sorry, forgot to say what the stable set is. Okay, the stable set is, this is the set of all the r's in C2 such that when I iterate them, the distance from f to the k of r to q is going to 0 as k goes to plus infinity. Okay, I'll just mention for unstable manifolds, unstable means as time goes to negative infinity. Okay, so the word unstable is a misleading word. It means stable for backward time. Okay, now, what does a stable manifold theorem say? It says that this, see, a priori, this is just a set, some strange set, you know, looking like a definition of a basin, more or less. But the stable manifold theorem says that this thing is, in fact, a nice manifold, and in fact, it'll be uniformized by some holomorphic psi that has the property that psi of 0 is q. So I can make, you know, my uniformization, take the origin to q, and if I take a point zeta and multiply it by this eigenvalue, that'll be the same as f of psi of zeta. Okay. So it tells me that I have a uniformization by C, so in terms of being a Riemann surface, I know it's equivalent to C. And on C, I know that f looks like something linear, and otherwise it comes in like this. Okay. So suppose we have, for our Henon map, suppose we have a saddle point. Okay. Then we have a stable manifold. So the stable manifold is sitting in C2. The question is, well, we know locally, locally we know what the tangent is, and locally a manifold looks like its tangent plane, so locally we know what the thing looks like. But suppose you go globally, what is the large term, large space behavior of the stable manifold? Well, there's a theorem, okay? So we're clearly going to work with currents. So let's take a piece of this. How about a yellow piece? I'm liking yellow. Okay, let's take a little piece of this. And I'm going to call this a stable disk. Okay? Now, if I take this stable disk and I map it backwards, well, I know that's the same as inside of C, just dividing by lambda to the s. I know that if I map it backwards, I'm going to fill out the whole stable manifold. Okay? So here's a theorem. So I want to apply F inverse, say minus n, to this stable disk. Okay? And I want to look at that current of integration and divide by degree to the nth. Okay? That's the same as, well, so in other words, I'm looking at this piece of stable manifold, and the theorem says that this is going to go to some multiple of mu plus, the same mu plus as before. And of course, it's important that C is strictly positive. And of course, the size of C depends on how much disk you start with. Okay? So I should say that here we have Q inside of our stable disk, and it's a holomorphic disk. You know, it's some disk inside our stable manifold. And so this goes to that. So this is an example of. I knew I was trying to answer a question of yours. It's answering the question of, are there other things that converge to mu plus? Now this has a very interesting consequence. The consequence is that if I take the whole stable manifold, this thing is dense in J plus, for instance. Okay? And well, it's not a closed submanifold, but it's a maybe we have different definitions of submanifold.
I'm just taking my algebraic geometer hat on.
Okay. So it's a
It's an immersed submanifold.
immersed submanifold. Well, it's okay. Immersed submanifold. Yes. Okay, immersed submanifold. But then I have to change the name of my theorem. The stable immersed submanifold theorem.
It's fine. It's just one.
Yeah. No. I'm sorry. I'm sorry. Yeah. But thanks. Yeah. So this is an immersed manifold, and so what this means, this second theorem, means that if I start with some saddle point. Okay. By the way, it's not so hard to see that all saddle points have to be inside of J. Maybe it's a theorem. Okay. Anyway, I start with the saddle point, and here I'm moving around inside of J plus, inside the boundary. So what this tells me is that as I'm moving around inside the boundary, I could go out and then come back and then come out. But whatever I'm doing, it has to come. And so this, in other words, we were saying the stable manifold. The stable manifold has to be dense in the whole boundary. Okay. So that means that. Okay, what does that mean? Okay. So that has an interesting consequence. Okay, it tells you, for one thing, it's not closed. Its closure is all of J plus. What's another consequence? Okay, if I take a different saddle point, and it's a theorem that there are infinitely many saddle points, then the other saddle point also is going to be in a different place, some place over here, some place. I have some other saddle point. Anyway, its stable manifold is going to come around here, and it's going to be dense too. Okay, these things are both dense, which is a way of describing a certain kind of chaotic behavior. It says, so this is Q1 and that's Q2. If I take any point here inside of J plus, if I take some point here, I know that infinitely close there will be something blue, and that'll take me back to Q1, or else something orange when I iterate it forward, I go back to Q2. So in other words, it's saying that all of the stable manifolds are sort of rubbing up against each other. Okay? And to answer Misha's question just a little bit more, so this was what we got by taking a stable a saddle point and looking at the stable manifold. We could also take, whoops, I didn't want to erase that. Okay, so we could also suppose this is an attracting. So it could be an attracting periodic point. But I can pass to f to the n. If I want to study one particular fixed point, periodic point, I can pass to f to the n and assume it's fixed. And that would mean, suppose I take the derivative at this point. Let me just write it this way. Let the derivative be contracting. Okay? So what that means is, this picture here, I could have some attracting fixed point in here. And I would have the basin of star. That would be all the points that are attracted there. Okay? Now it's a theorem that, speaking holomorphically, basins of attraction are biholomorphically equivalent to C2. I could ask myself, well, what is the boundary of the basin? So let me focus once again here. So here's my basin. And here is star. Now for convenience, let me suppose that the differential here has eigenvalues lambda and mu. Suppose, say, that lambda is less than mu, and that's less than 1. Okay? So there's also a version of the stable manifold theorem that says if I have one direction that's smaller than the others, I'm going to have a strong stable manifold coming through there. So I'm going to have a similar kind of thing here. This will be a strong, stable manifold through star. Of course, everything is in the stable set. The whole basin is in the stable set. But these, I'm going to have a manifold of points that converge faster. Okay, these are the points that converge faster. So instead of saying the distance converges to 0, I would say the distance is looking like lambda to the k. Okay? And that would tell me that specifies this, for the strong stable manifold, that specifies a submanifold. And I could ask myself, well, let me take a disk inside of here. Okay. What happens if I should say strong stable. Okay. What happens if I start mapping this disk backwards? Okay. It's going to be moving around. Okay. Has to stay inside the basin. It's going to be uniformized by C. And so I keep coming back and coming back. And in fact, sort of the thing it's going to do is it's going to start sort of accumulating on the boundary, and the theorem is this. So I'm going to start pulling this thing back and look at that current of integration, divide by the degree. Okay. Well, there's nothing for it to converge to. The only possibility is going to be some multiple of mu plus. And so that means that when we take the limit, the limit current, its support is completely disjoint from the original manifold. So just by the way, support of mu plus, the limit intersected with the whole strong stable manifold is going to be disjoint. Okay? Because the strong stable manifold is contained entirely in the interior of this basin, the support of mu plus is entirely in the boundary, or is the boundary exactly. Okay? So that's amusing, okay? But the sort of the reason for looking at this is the conclusion, as we have the corollary, is that the boundary of the basin is J plus. Okay? In other words, I know that for any point of J plus, I can approximate it. I can come arbitrarily close by a point, you know. So, the point here is these, is that I've got DSS, and I keep getting larger. In other words, I've got something increasing, okay, and I fill out, you know, the union of these guys will be all of this thing. So I know that for everything in the basin, and rather everything in J plus, I've got to have some WSS pretty close because this current is converging to that. So I have to have, for any point in the support of this, I have to have some of this close by. So that tells me that the boundary of the basin contains J plus, okay? But on the other hand, I know that the boundary, that the basin of star is an open component of K plus. So this is an open component, so its boundary will be inside the boundary of that. Okay. So the conclusion is that they're equal. Okay. Now, is this surprising or worth stating or not? I think it's pretty interesting, okay, because there's this Newhouse phenomenon. And it says there would be quadratic in other words, f of, you can choose parameters, so you would have x squared plus c minus delta y with real coefficients here, with infinitely many sync orbits. Okay. So what is that telling me then? Oh well. What's telling me then, you know, so therefore there exists f such that I've got basins, basin 1, basin 2, basin 3, etc. And they all have the same boundary. Okay, so that tells you, in particular. So, if I had one basin, I could draw this picture here, and it would be, in fact, it's been proved that this picture that I've drawn corresponds to some actual maps. But if you've got two basins, if I try to draw that in this picture, I've got a little bit of trouble here because I have to have two basins with the same boundary being also J+. So I have to have things sort of mixed all up. It's I would think of it as being, you've got a pot with a whole bunch of, you know, like 2 or 3 infinitely long pieces of spaghetti, and the ends are getting thinner and thinner, and they're all sort of, you know, getting close to each other. Okay, so so I have to now.
I mean, there is any number of basins.
Well, there can be, yeah. Newhouse did a couple of things. One of the things he showed was that for certain, there are real quadratic maps with infinitely many sync orbits.
Yeah. It's impossible in dimension 1 there.
Yeah.
Oh, right, yeah. Mm-hmm. Yeah, I have not mentioned critical points, and Misha didn't say too many things about critical points, but in dimension 1, every basin has to own a critical point. And so there's some very specific bound. Now, There are several things I could say, and so I need to figure out what to say. Let me just say, where does mu plus come from? Okay. Well, Misha told us where mu plus came from. This comes from the same place that Misha was telling us about with Brolin's theorem. Oh, I erased the picture I was going to talk about. Okay, so we still have our filtration, okay? And here we know, I want to use the notation, if I take the nth iterate of xy, I'll call that xn, yn, okay? This is my orbit. I'm here going to infinity. I've got some point xn, yn. And at every stage, I'm raising it to the dth power. So I know that xn is going to be looking like e to some g times d to the n. Okay? And this g was the green function for Misha, and it'll be the green function for me too. So let's define g plus of xy. I can define it this way. Since xn is getting much bigger than y, this would also be the same as n going to infinity. Well, it doesn't make any difference here, degree. For any norm, okay. So I have a g plus here, and I should say here with maybe blue color, I could also make a g minus, where I would have the backward orbit, okay, or else minus. Okay, so for okay, so I'd also have a rate of escape function in backward time. So the theorem is that this limit is uniform, this limit here is uniform on compact subsets of C2. Okay. And we have, let me just write G plus, looks like log mod x for large x. It looks like 0 on k plus. Oh yeah, and the other thing is, of course, the fundamental thing is that if I take g plus and compose it with f, okay, then I've got an extra n, and I'm missing an n there. I'm missing a degree there, so this would be the degree times g plus. Okay, so these are the... Oh yes, and it's pluri-subharmonic, right, exactly. Pluri-subharmonic. So in fact, what happens now? Let me just look at this picture. Okay, so in fact what happens is that if I take any plane, or this is a complex line, so I'm going to intersect along some place here. Okay. So this is any complex line. Then, in fact, if I look at g plus on this line, this is the same as the green function for k plus intersected with the line inside of the line. In other words, I have a copy of C here. I could intersect with this, okay, and I get a green function. The dynamics does not restrict. No. But I'm sort of internally doing a victory dance because this means now you can do all sorts of potential theory things. And so, so what do I want to say here? I'd like to say something. So the thing is, this function g plus, since it's plurisubharmonic, can look like a potential for this current mu plus. So what is the story with potential? Well, the relationship is, as Misha told, well, let me see. What I want to do here is approach things a little bit more slowly here. So if I look at D, that's the partial with suppose I'm in C with a variable w, which would be u plus iv. Let me back off to dimension 1. Okay? Then D on C would be the same as the partial with respect to u times du plus the partial with respect to v times dv. And then I want to look at the one form that I get multiplying by I. So, okay. So if I multiply du by I, it moves around to dv. And then if I move dv, it moves around back to minus du. So like that. Okay. So if I take d dc, I'm going to have du squared plus dv squared, and then I'm going to have uv. So I'm going to have a 2. Okay. So this is the thing that gives us the you can view this as using the complex structure to give us the Laplacian in one variable. Now what about two variables? I want to do the same thing. I have d, and I can multiply it by I and get dc. And so if I take ddc, this is going to, well, I can just in general, just permit me to write it this way. Okay. So what does ddc do? Well, what happens in one variable? Well, this is essentially the Laplacian. Although there is some, we are in a different degree, but if we take the Laplacian of log mod w, we're going to get 2 pi times the point mass, where let me just upgrade and call it the current of integration over 0. Okay. And so what I want to say over here is the Poincaré-Lelong formula. And that says that suppose I take d dc of log y. So I'm taking the second variable in C2, divide by 2 pi. I'm going to get the current of integration over y equals 0. Okay. So this is, here I start out with a scalar function. Well, let me not get into that. So I have y equal to 0 like this. And so, so my current, mu plus, in fact, is going to be 1 over 2 pi d dc g plus. Let me just tell you, that's exactly what I'm going to have for d dc g plus. Now, this first theorem here can get upgraded, okay, to something that looks sort of similar. Like this. Okay? So I've just now made a major change in the theorem. And the reason is, well, I actually didn't define log plus. Log plus of something or other is the maximum of 0 and log t. Okay. Here I just have log. So actually xn, if xn is very small, I'm going to get some logarithmic pole. And so here, to be able to discuss this, this is not continuous, so I need to discuss what's the sense of convergence. Will it be an L1 loc? Okay. In other words, the L1 loc is a nice thing to converge in. And so so what is this doing for me here? So if I converge an L1 loc, if I'm going to use currents are like using distributions, and you know that one of the virtues of using distributions is that you can always differentiate them. Okay, so I can differentiate this thing, so I'm going to apply 1 over 2 pi ddc. Okay, I'll apply 1 over 2 pi ddc to this thing, and so what I'm going to have here is, by the Poincare-Lelong formula, I'm going to have 1 over degree to the n times the current of integration over xn equal to 0. That's what I get on the left hand. And on the right hand side, I'm going to get mu plus. Okay. Now, what is xn equal to 0? Well, this is exactly just f to the minus n of x equal to 0. Okay. So this is, if I could prove this theorem, then this would be the theorem that gives me Brolin's theorem, or the analog of Brolin's theorem. And I just have a minute left here. So let me say one other thing. What would have happened?
Are you using this one to prove that one, or?
No, I'm saying that this is I'm saying that this is a super easy theorem, and this theorem takes some proof. Okay, I mean, this theorem here is I could give you a proof, but this one is super easy because there are sort of two cases to consider. If xn is going to infinity, it's really easy to see what's going on here. If xn stays bounded, well, the log plus just means, let's just call it 0. We're going to be dividing by something that vanishes, so it just is going to go to 0. So the issue that's controversial is, suppose xn is small. Okay, that's the issue. So one way of seeing this is, what is ddc of log plus of y? Okay, what's the difference? Okay, between, I told you dd by the Poincare-Lelong formula. Okay, that thing, in other words, I have a logarithmic singularity that gives me the current of integration over the 0 set. Okay, what happens if I max with 0? Okay, well, if I'm looking in C with my variable being w, if I look at log mod w and take the Laplacian, I'm going to get the point mass, the current of integration over the origin. Okay, if I look at 1 over 2 pi log plus of w, well, what's happening here? I've got the unit circle. This thing is just 0 inside. It's harmonic outside. And what I get around here is just normalized d theta. Okay, so what happens if I do this? Well, I'm going to look at my y coordinate. I'm looking here where modulus of y is 1. And for y fixed, I have the line y equals e to the I theta. Okay. And so what I get here, in fact, is a smoothened current. Okay, I get the currents y equals e to the I theta. 2 pi. In other words, you can take currents of integration and sort of average them. So this would be the current I would get by taking the integrations over these lines and then just averaging them over the transversal circle. So I think I've given you a slight clue as to what this limiting for Bernoulli's theorem. I've given you a clue as to what the limiting current is, some way of defining it here. And I think I've used up all my time. So thanks for listening.
Any questions? Well, thanks again. Now there's lunch in the